Hi, this is Chris. So today I'm going to present Paxos algorithm. Paxos algorithm is a consensus algorithm to solve a problem with the following conditions. At first, in the consensus, only the value that has been proposed may be chosen, which means the only way a value can get into the system is either a node proposes one or it receives one from others. There's not a third way for a value to get into the system. The second is only a single value is chosen, which means they need all to agree on a single value. And the third one is the process never learns that a value has been chosen unless it has actually been. It means that you cannot basically pre-code the values into the processes. They have to communicate with each other and make a decision. We have the following assumptions for the algorithm. The first one is the network is asynchronous. The second one is the network is arbitrary topology. The third one is we are in a timing model of unbounded delay. And the fourth one is the fail model. The fail model is the processes can fail and they can restart, but it's in a non-biased model. We also model each process to have three functions. The proposer to propose values to others, the acceptor to accept values from others, and learner to learn the final decision. To build an algorithm to solve the problem, we can first think what properties does this algorithm need to have. We can find that for whatever algorithms, it must have the property 1 mentioned in the paper, which is an acceptor must accept the first proposal it receives. It is because otherwise, if you have only one proposer and it only proposes in one round, then if others don't accept the first proposal, then no decision could be made. So in the algorithm, they must accept the first proposal that it receives. With only property 1, we have actually already solved the consensus problem when there are only 1 or 0 proposers that is proposing. All the following effort, as well as the property 2 in the paper, are just to solve the problem that when there are 2 or more proposers, what should we do? We can just forget about the paper for now and consider that there are actually only 2 subproblems when there are 2 or more proposers in the system. The first problem is that each proposer may pass message to a bunch of distinct followers, which is receivers, but no majority actually exists. It's a bit like partitioning. Like see the picture, this masked cat passed on message to this cat, and this green cat passed a message to another cat. Now we have 2 cats have one value, the other 2 cats have one value, and the left one cat has a value. So there are no majority. The second problem is that a process may receive multiple proposals from different proposers, so that it doesn't know what to do. For example, in the picture, this cat receives different proposals from this masked cat and this green cat, and it doesn't know what to do. We consider problem 2 first. There are many ways to solve it. Here, we consider that if a proposal with value v is chosen by a process, then every subsequent proposal within the logical time that is chosen for this process has value v, which means that, for example, the masked cat sent 1 to the right cornered cat, and then the green cat sent 2 to the right cornered cat. The cat will reject the message from the green cat because it have already received 1 from the cat above. This defines the behavior when multiple different proposals are received by different proposers, which is basically to stick to the earliest one. Now with the property 2 we can try to solve problem 1 with a theoretical solution. Well, the solution is just to capture the behavior of the system that is required to solve problem 1. It may not be implementable directly. We see that if a proposal with value v is chosen, then every higher numbered or every subsequent proposal chosen by any other acceptor has value v, so that this property ensures that there will be no processes that have different values when one of the values is secured by a process. So that it solves the problem 1 when different groups hold different values, but there's no majority. What does this problem related to Paxos algorithm? We see the solution to problem 1 and solution to problem 2. Adding them together is actually P2, the priority 2 in Paxos. And P2A basically stated the same thing with P2, it just changed the word from chosen to accepted. Since problem 1 plus problem 2 solves basically everything, so the P2 in the Paxos algorithm solves everything basically, and P2A lead to P2, and P2B lead to P2A. But what's P2B? Remember that we mentioned the solution to problem 1 is not very implementable. Therefore, P2 is not very implementable in Paxos. So does P2, P2A. Therefore, P2B is an improvement. We say we want all processes accept value V when there's one process accept value V. We know that the value cannot appear from nowhere. In the condition of the problem, it's either someone send it and I receive it, or I send it. So we can ask the proposer to only send V to make sure that the acceptors can receive V. Right now, the properties are generalized description of the behavior of the whole system, because you see all the subjects are either all the proposers or all the receivers, all the acceptors. So P2C describes the system in micro scale. It describes what will happen when a pair of processes communicate with each other. Speaking in a simple way, it describes the following things. The first is that majority is enough, which is very intuitive. We don't need to all processes to have the same value. As long as the majority have the same value, it's okay. The other thing is that it mentions the three cases when a proposer talks to a acceptor. As long as the system always behave in these three cases, the whole system will be correct in consensus making. The first is outdated. The proposer sends an outdated message to the acceptor. Outdated means that the clock of the sender or the proposer is smaller than the scalar clock of the receiver, so the receiver doesn't need to care about this message. The second is not received before, which means the acceptor haven't received any proposals before, so that it just accepts the message from the proposer directly and take the value. The third case is update newest V, which means that the acceptor has already got the newest value V from whatever proposers. Then when a new proposer wants to propose a value, the acceptor tells the proposer that it has already got the V and asks the proposer to propose this value V to others. You see that the first case and the second case combined together is the condition A mentioned in P2C, and the third case is actually the condition B in P2C. Therefore, from P2C, we can derive implementation directly, which is described in the paper, also illustrated in this picture. So the green cat is the proposer. It will first enter the prepare state, where he sends the prepare message with his clock to all the learners, all the acceptors. And assume that his message is n equals to 5. And the top cat here, his n value is 0, so he changes value n to 5. He hasn't got any values, so he accepts the value 10, and he makes the promise that he will now his time is 5 now, he will discard all the message with time below 5, which is the same to scalar clocks. The cat in the middle have value n equal to 10, so it doesn't care about this proposal. The cat below has n equal to 4, so it updates to n equal to 5 and made a promise of not accepting any proposal with n smaller than 5. But it has a value v equals to 19, so it sent 19 to the green cat, the proposer. Then after the green cat gathers the majority of the response, which is 3 out of 4 now, including itself, he can send an accept request to all the cats. And the value v is 19 because it's the value updated from the receivers, the acceptors, and the time n equals to 5. Still, the masked cat will still not going to accept it, but it doesn't matter. The majority is already reached. If the majority does not reach, the cat may increase the clock and try again. When the cat has a clock greater than 10, then the proposal may be accepted and the consensus may be built. All other cats may have the start to raise proposals. Because you see the cat has a clock 10, which means there must be some cat with clock 10 that is proposing or greater than clock 10. How do we map the implementation to the property P2C? So we can see here the masked cat means outdated in the three cases we mentioned because it has higher clock value. The cat in the middle means not received before in the three cases because it hasn't got any value before and the first proposal it receives. And the cat in the bottom means the newest V in the three cases. It has the newest V and updated to the proposer to broadcast to all else processes. Now the algorithm is almost finished. We will just make two patches here. The first one is learner. Learner is just to learn the decision of the majority got by a proposer, then dispatch it to others. The second one is the distinguished proposer. Consider the case when there are only two nodes keep sending prepare requests to each other. So the clock number will keep increasing, but no consensus will be made. It's a very special case, but to prevent such a case, we need to elect one proposer to be the only proposer that's pass on messages. We don't care about what election algorithm we use. We cited the work done by other people. It's a magic election algorithm. When we have successful election and we have no failure, the whole system just downgraded to only have property 1. That is, as long as we have property 1, we can solve everything. So basically, all the property 2 and following Paxos algorithm is just to solve the cases when there suddenly appears more proposers. Now we get some demos, although we have already actually given one. The first one is very easy. There's only one proposer selected by the selection algorithm. It then prepare a message to all the other people. Other people receives with that promise not to accept any message below equal to 1. And since no value has been decided before, the proposers can propose whatever value it wants and tell all the others. Then decision is reached. Now let's see the demo 2, where the leftist cat in the green circle receives 2 messages. There are actually 3 cases here. The first one is that the cat receives this prepare n equals to 1 first, then it responds with a promise. Then the top right corner cat send accept the request. Then the cat in the green circle accept it. Then the decision has been made. Then finally the prepare message from the bottom right cat reached to the cat in the green circle. Well, the cat in the green circle just discarded because the decision has already been made. The second situation is that the prepare n equals to 1 message reached first, and the prepare n, we say now n, for example, equal to 0, reached secondly, but before the cat accept the request from the top right cat. Therefore, the cat just ignores the prepare n equal to 0 because it has already got n equal to 1. The third situation is that the message in the bottom reaches first. Assume it's still prepare n equals to 0, and the protocol between the cat in green circle and the bottom cat has already established. The bottom cat passed the value 5 to the cat in the green circle. Now the cat receives the message from the top right corner cat. It will accept the message because n equal to 1 is greater than n equal to 0. But since it has already gotten a value, which is 5 proposed by the bottom cat, it will pass this 5 to the top right cat, and the cat will broadcast this 5 to this masked cat, so the decision is still reached. So that's basically it. Thank you very much.